This is GARIS Essays, that is 2 3-page opinion pieces on topics such as species dominance, the global state, politics, femtotech, religion, society, and education. Written by and read aloud by Prof. Dr. Hugo de Garis. This is essay number 34, entitled Topological Quantum Computing, that is TQC. The TQC shockwave and its impact on university computer science teaching, by Prof. Dr. Hugo de Garis, Director, Artificial Brain Lab, that's ABL, Cognitive Science Department, School of Information Science and Technology, Xiamen University, China. Email profhugodegaris@yahoo.com. Abstract. Topological quantum computing, TQC, promises to make quantum computers robust and hence scalable in the next few years. Quantum computers are exponentially more powerful than today's classical computers, so a successful TQC will revolutionize computer science, necessitating that the principles of TQC be taught in thousands of computer science departments around the world. Unfortunately, understanding these principles requires a PhD level knowledge of topics in pure mathematics and theoretical physics. Since most university computer science departments stop teaching math and physics at undergraduate level, the need to upgrade their teaching of these fields to PhD level will generate shockwaves in their teaching policy and faculty hiring. This article shows how a pioneering university in southern China is coping with this problem. The idea of quantum computing, QC, with its exponentially superior computing capacities compared with classical computers, has been around for a quarter century. Reference Feynman, 1982. However, storing a quantum bit or qubit of information in a very small region, for example on the spin of a single electron, makes such storage highly vulnerable to disturbance from the environment, a phenomenon called decoherence. Reference Nielsen and Chuan, 2000. The new topological quantum computing, TQC, reference Collins 2006, Day 2005, Das-Sama et al. 2006, stores the information topologically, that is globally, in the topological invariance of topological quantum fields, and is thus far more robust against noise, making quantum computing practical, using phenomena in the fractional quantum Hall effect, FQHE. Reference Van de Grit, DEGRITT et al. 1992. However, teaching computer science students the principles of TQC implies that they be taught PhD level mathematical physics and pure mathematics. Computer science students will need to learn a lot more mathematical physics. This will make the study of computer science a lot more intellectually demanding and give it a higher status than it enjoys today. University computer science departments will have to hire or collaborate with professors in pure mathematics and in theoretical physics and change their curricula to adapt to the TQC revolution. Quantum computers. For many decades, computer scientists felt that computation was a branch of applied mathematics. However, in the 1980s, a new viewpoint grew up, namely that, quote, new physics implies new computation. This means that by employing new phenomena in physics, one can compute more powerfully than with traditional Boolean logic-based classical computing. By exploiting the quantum mechanical phenomenon of superposition and entanglement, it's possible to perform quantum computing, which can calculate 2 to the power n things simultaneously, where n is the number of quantum bits in the computer's quantum register, and thus vastly outperform a classical computer, which can only calculate one thing at a time. If quantum computers can be built successfully and with large N, then our whole culture will be changed radically. For example, biology will be revolutionized because quantum computers will be able to simulate large molecules and even cells. Classical computers cannot simulate large molecules because they cannot simulate large quantum systems. For example, every time one adds an atom to a molecule to be simulated, that molecule's Hilbert space, in quantum mechanical terms, doubles in size. Quantum chemists can only use classical computers to simulate small molecules, but with quantum computers, every time one adds a qubit to the quantum register, the number of calculations that register can perform simultaneously doubles. Hence, as the size of a simulation problem doubles by adding another atom to the molecule, by adding another qubit to the quantum register, so too does the computational capacity of the quantum computer. Therefore, quantum computers can simulate large molecules. As n increases, 2 to the n becomes astronomically large. Hence, one can imagine simulating DNA molecules, protein folding, cellular components, whole cells, organs, etc. Our whole technological culture will be changed radically given the exponentially superior computational capacities of quantum computers. Decoherence. However, this dream of exponentially superior quantum computers has a catch, and that is that quantum computers, as they've been conceived until recently, are fragile. In a traditional quantum computer, a quantum bit or qubit of information is stored highly locally, for example on the spin, up or down, of a single electron. This form of highly local information storage is particularly vulnerable to disturbance from the environment. That is, other atoms and fields in the neighborhood can interact with the electron and change its state, thus losing the information stored in that state. Quantum error correcting codes were invented in the mid-1990s to correct such errors. Reference Shaw, 1985. But only if the probability of error was very low, that is about 1 part in 10,000. In practice, this is very difficult to achieve. So after a quarter century since the invention of the idea of quantum computation, we still do not have operational quantum computers with large n. Topological quantum computing, TQC. But in 1997, a Russian mathematical physicist, Kitaev, that's Kitaev, Kitaev, conceived the idea of using a so-called quantum topological field, reference Kitaev, 1997, to store information in the topological invariance of that field, that is, spread out over a wide region, so that if the environment were to disturb a portion of the field, the information stored in that field would not be changed. It would be robust against noise. As a simple example of a topological invariant, consider a rubber figure-of-8 donut. By squashing it, twisting it, the angles and lengths change, but there's a topological property of the object that remains invariant, and that is the number of holes it has, its genus, G-E-N-U-S, to use the technical term in topology. In 2000, Michael Friedman, a Fields Medal winner for his work in topology in the 1980s, invented the mathematics of a method for performing universal quantum computation using a topological quantum field, reference Friedman et al. 2000. Thus the theorists had provided a new approach to quantum computing that in theory at least could overcome the decoherence problem. Anyons, that's A-N-Y-O-N-S, anyons. The next step, now hotly pursued, is to find phenomena in physics which obey Friedman's mathematics. The favourite candidate is the so-called 12/5 state in a phenomenon called the fractional quantum Hall effect, FQHE, reference von de Graaff et al., 1992, in a specialty known as condensed matter physics. The FQHE, fractional quantum Hall effect, arises when free electrons sandwiched between two layers of gallium arsenide are subjected to extreme cold and to an extremely strong transverse magnetic field. These conditions cause the electrons to agglomerate into so-called anyons, that is, quasi-particle excitations, which have weird properties, for example, fractional charge and non-fermion boson statistics. They are called anyons because they can have any statistics. From quantum mechanics, we know that when two fermions, or bosons, swap positions, the total quantum state is multiplied by -1, or +1. But for the anyons, things are more complicated. If the state of a line of anyons is represented by a quantum mechanical column vector, then when two anyons swap positions, the column vector needs to be multiplied by a matrix, and the matrix will differ depending on whether the two anyons moved around each other in a two-dimensional sandwich, clockwise or anti-clockwise. If one traces out the paths taken by two anyons as they swap positions as world lines, as in relativity theory, then the paths will look like a double helix, twisting either clockwise or anti-clockwise as one looks down on the upward moving helix. This spiraling of the anyon pair is called a braiding operation. A sequence of such operations over n anyons is called a braid. The set of all possible braids for n anyons forms a mathematical group called the braid group. Reference Jack, that's J-A-C-A-K, et al., 2003. Freeman and others showed that any quantum computational calculation can be approximated to any desired accuracy by performing a sequence of braiding operations on anyons. A sequence of braiding operations corresponds to multiplying the initial state of the anyons by the appropriate sequence of matrices. The longer the sequence, the greater is the possible accuracy of the calculation. In traditional quantum computing, an initial quantum state is multiplied by a unitary matrix to create a new state, which is then measured to give the result of the quantum computation. Thus, Friedman showed that any unitary matrix can be approximated by multiplying by the matrices that correspond to the sequence of braiding operations. I call these elementary braiding operations EBOs, or just EBOs. Bonesteel, or Bonesteel, B-O-N-E-S-T-W-L, et al., reference Bonesteel et al., 2005, found anyon EBO sequences that approximate the building blocks that can be used to perform any quantum computation. For example, single qubit phase change gates and the C-NOT, controlled NOT gate. Figure 1 shows elementary anyon anti-clockwise and clockwise braiding operations, EBOs, and their corresponding matrices. No, I can't describe this in words. You'll have to go to the text, read the text essay, which you can see on my website under essays. So figure 1, 2 elementary braiding operations, EBOs or EBOs, and their corresponding anyon quantum state changing matrices. There are 3x3 matrices there. Condensed matter physicists have already confirmed experimentally that the quasi-particle excitations of the FQHE, fractional quantum Hall effect, act as anyons. For example, the 5/2 excitation. It's also known that only non-abelian, that is, the two matrices A and B corresponding to two braid operations, do not commute. That is, AB does not equal BA. Anyons can perform universal quantum computation. The 5/2 excitation is non-abelian, but unfortunately is incapable of universal quantum computation for other reasons. However, mathematical simulations have shown that the 12/5 anyon is non-abelian and is capable of performing universal quantum computation. So the experimental condensed matter physicists are now feverishly conducting experiments to confirm that the 12/5 excitation is in fact a non-abelian anyon and hence could serve as the cornerstone of topological quantum computing, TQC. Not surprisingly, interest in TQC has skyrocketed now that it looks likely that a physical means to implement the already established TQC theory is at hand. Workshops on the topic have popped up like mushrooms in the past year or two in the US, UK, China, etc. Governments are starting to get interested, since if the condensed matter physicists confirm that computationally universal non-abelian anyons exist in reality as is strongly expected, then the prospect of implementing topological quantum computers becomes much more realistic. The creation of scalable topological quantum computers will have profound technical, economic, and cultural impact. The educational impact of TQC. But there's an educational price to be paid. Ordinary quantum computing, QC, is usually taught at senior undergraduate and/or first-year master's level, because the level of mathematics and the physics knowledge needed to understand quantum computing, QC, is at that level, for example, using linear algebra, Hilbert spaces, etc. However, TQC requires a much higher level of knowledge of pure mathematics and theoretical physics. For example, deriving the matrices that correspond to the braiding operations, EBOs as I call them, described briefly above, uses such notions as the R and F matrices and the pentagonal and hexagonal relations of quantum groups and conformal field theory, QFT, which is PhD level pure math and theoretical physics. Given the critical importance of TQC to humanity's future, computer science departments at thousands of universities around the world will come under pressure from national governments to teach the principles of TQC. And this in turn will send shockwaves through these departments as they come to terms with the reality of the level of difficulty of the pure math and theoretical physics needed to teach it. As a consequence, computer science, CS, as a specialty will quickly gain a new reputation, that is, as being one of the toughest and most intellectually demanding specialties on campus, comparable with that of pure mathematics and mathematical physics. In fact, CS, computer science, will need both, as well as the usual notions of computing. In time, the status of computer science as a specialty will rise, as the average intelligence level of the students studying it rises, as it must. Today's average computer science graduate student will not be able to cope with the high level of mathematical abstraction needed to understand such TQC topics as quantum groups, conformal field theory, quantum field theory, topological quantum field theory, algebraic topology, etc. TQC courses. Computer science departments will have to hire or collaborate with pure math and mathematical physics professors to teach TQC-related topics. Computer science deans and heads of department will have to restructure their computer science courses, and so will need guidance on how to do this. What now follows is a list of those topics that will need to be taught in computer science departments in order for graduate students to understand TQC, topological quantum computing. It includes a detailed timetable of the TQC type courses that were originally planned to be taught at my university, that is Xiamen, pronounced Xiamen University. XI in ad-libbing now. XI in Chinese is a sh sound, as in she. That is Xiamen, pronounced Xiamen University in the south of China, not far from Hong Kong. These pipeline courses take 4 years. For example, a 3 years master's course plus 1 year of PhD, or a 2 years master's course plus 2 years of PhD. See Figure 2 for details. This timetable and course list may be useful to deans and department heads who are considering doing something similar for their universities. In China, it is referred to as the Xiamen model for TQC teaching. I now have a problem because I'm reading this aloud. This is verbal. And the first figure shows 8 semesters and the abbreviations of the topics to be taught. And they don't mean much. Like, for example, Year 4 and plus Semester 2, PhD M8, so that'd be the 8th semester in mathematics at PhD level, stuff like that. There's a whole table of it. If you want to see the details, go to the text of this essay on my website under Essays. The above table requires some explanation. The capital M refers to a master's level course. The PhD refers to a PhD level course / seminar. The little m following a big M refers to a math course, and a little p to a physics course. The numbers refer to the semester number over 4 years, that is 8 semesters. For example, capital M, little p, 3 is the master's level course in physics in the 3rd semester. At my university, our strategy was that I would teach all courses at least once to give me experience of all the TQC-based courses. However, since the courses are pipeline over 4 years, if I were to teach all courses, the total teaching load would become unreasonably large. So I teach each new course once, then pass it the following year to a colleague in the math or physics department. However, I do teach the quantum computing course in MP3, and the topological quantum computing and condensed matter quantum field theory course in MP6, and all the PhD TQC courses. The courses in Figure 2, in italics, in a given year are taught by professors in the math or physics department after they've been taught once by me. Courses in bold, in a given year, are taught by me in that particular year and for the first time. Courses in bold italic are taught by me permanently. Students are offered the TQC/MPC, that's Topological Quantum Computing, Math, Physics, Computing, specialty as an orientation. Once they enroll in it, they commit themselves to spending 3 years of their master degree and a further year or two in a PhD program if they continue to a doctorate degree, taking TQC/MPC courses. The first year at the master's level is a prerequisite year in which computer science students learn topics from undergrad level math and physics that are needed to understand TQC. Math and physics students are allowed to take the courses and get credit. The actual contents of these courses are now listed. Each course is for 3 lecture hours per week for about 18 weeks. Year 1, first semester, Math, big M, little m1, vector analysis, real analysis, complex analysis, Fourier analysis. Physics, that's big M, P1. Electromagnetic theory, special relativity, statistical mechanics. Second semester, Math, big M, little m2, finite group theory, differential geometry, basic topology. Physics, MP2, analytical mechanics, quantum mechanics. Year 2. Once the TQC/MPC orientation master students have completed their first prelims year, they then begin more serious study of TQC/MPC topics at master's level. Third semester, Math, MM3, algebraic topology. Physics, MP3, quantum computing. Fourth semester, Math, MM4, Lie groups, algebras, and representations. Physics, MP4, general relativity. Year 3, fifth semester, Math, MM5, knot, that's K-N-O-T, knot theory, braid groups, etc. Physics, MP5, quantum field theory, that's QFT. Sixth semester, Math, MM6, manifold theory. Physics, MP6, topological quantum computing, TQC, condensed matter quantum field theory, CM/QFT. Year 4, PhD level and beyond. At my university, about half of the master's students continue into a PhD program. PhD level TQC/MPC courses take the form of weekly research seminars in which students study and discuss advanced textbooks and research papers on the following topics. Math, PhD M 7 and 8. Conformal field theory, CFT. CATS, KAC, Moody algebras, operator algebras, quantum groups, etc. Physics, PhD P 7 and 8. Topological quantum field theory, TQFT. Advanced topological quantum computing, TQC. Gauge theory, string theory, etc. 2 years of teaching TQC, lessons learned. This section was written October 2009, 2 years after the paragraphs written above in this article. It describes the actual experiences of the author in teaching TQC courses to master's level math, physics and computing. I moved to Xiamen University, Xiamen, Fujian Province, China, early in 2008, and under contract I started to teach a set of TQC courses, similar to those mentioned above. I had been told before I moved to Xiamen that the master's course at Xiamen University lasted 3 years, so I prepared the TQC courses to be spread over 3 years, as shown in the above section. When the time came to actually start teaching, the person in charge of organising the teaching roster for the school explained to me that in fact there was only half that time available. I was then forced to compress the set of TQC master's courses to last only 3 semesters, so the new plan that was concocted is shown below. Master's level TQC courses, Year 1, first semester, Math, MM1, an accelerated prerequisite course of undergrad level mathematics topics, finite group theory, complex analysis, Fourier analysis, differential geometry. Physics, MP1, an accelerated prerequisite course of undergrad level physics topics, special relativity, electromagnetic theory, statistical mechanics, analytical mechanics, quantum mechanics. Second semester, Math, MM2, manifold theory, algebraic topology. Physics, MP2, quantum computing, general relativity. Year 2, third semester, Math, MM3, Lie groups algebras, representations, braid groups, knot theory. Physics, MP3, quantum field theory, QFT, topological quantum computing, TQC. PhD level courses. Those students wanting to do a PhD in TQC can attend seminars in later years in PhD M1, conformal field theory, CFT, Kac-Moody algebras, etc. PhD P1, Topological quantum field theory, TQFT, Advanced topological quantum computing, TQC. PhD M2, operator algebras, quantum groups, etc. PhD P2, gauge theory, string theory, etc. What actually happened? From the courses mentioned in the above list, one sees that the first two courses, taught in the first semester, were effectively an accelerated introduction to essential topics in undergraduate math, finite groups, complex variables, Fourier analysis, differential geometry, and to undergraduate physics, special relativity, electromagnetism, statistical mechanics, analytical mechanics, quantum mechanics. The following semester I needed to devote more time to my primary research activity, that is artificial brains, so I only taught one course. It was the physics course, which crammed both quantum computing and general relativity into one semester, that is double the usual rate. Not surprisingly, I suppose. The only people in the class, only a handful, were from the physics department. The computer science students, who had been in the previous semester's classes, felt that such obvious and difficult physics subjects were not particularly relevant to their near future computer science careers. Mostly they thought that the master's physics courses, especially general relativity, were too difficult for computer scientists. At the time of writing this section, October 2009, I am currently teaching an artificial brains course to master's students, something that I need to teach once a year. Hence, in practice, my TQC teaching has been reduced to half the rate at which I had originally planned, that is, only one course instead of 4 per year, but taught at twice the speed. TQC grad students will need a minimum IQ of 150. It's generally thought amongst mathematical physics researchers and professors who specialize in TQC that a minimum IQ of about 150 is needed to be able to fully master the material in TQC. For example, particularly difficult topics such as conformal field theory, quantum groups, advanced algebraic topology, topological quantum field theory, etc. An IQ of 150 is roughly that of university professors in the sciences. In the US, the average IQ of theoretical physics professors is 170, that is 4.7 standard deviations above the mean. It is these high IQ levels required for TQC mastery that is the source of the TQC shockwave mentioned in the title of this article. This greater intelligence level that is required is also the reason why the general status level of computer science will go up significantly in future years. The best master's students in theoretical physics and pure mathematics at top universities in China, such as Beijing University or Tsinghua University, would have those ability levels, whereas the average master's students in most of today's computer science departments around the world will not have such levels of intelligence. Therefore, speaking bluntly, most of today's computer science master's students are simply not bright enough to study TQC, hence the shockwave, as computer science deans and department heads come to terms with this new requirement. We will probably have to wait until TQC has become a reality, that is, that large N quantum computers have been built, and for ministers of education and technology around the world to start putting real pressure on the best universities to teach TQC. Only then will pressure be placed on the best students to move into computer science instead of theoretical physics and pure mathematics, as is largely the case today. As a result of that pressure, computer science departments will see their general prestige level rise, for the simple reason that the topics they teach, that they have to teach under severe pressure from government ministries, are a lot more intellectually demanding than they were before the TQC revolution. Computer science students will be smarter, and so will their professors. Computer science will become as prestigious